Hello and welcome to this revision session for AQA A-Level Physics Paper 2, looking at the topic of thermal physics. So in today's revision session we're going to look at how to answer examination questions on A-Level Physics Paper 2. So if we've been successful and we've learned in today's lesson, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? When you're completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. In this left hand side section, write down your working out and answers to the question in the revision session. When you're doing this, make sure you write in full sentences and show your full working out. Whilst in the right hand side, write down any piece of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising for A-Level Physics? So the first thing to be doing when you're revising independently for A-Level Physics is learn the key facts. Use revision guides, the class workbooks, the student prep notes, the textbook to learn the key ideas of the course. You might wish to make mind maps or to write out notes yourself. The second step is to test yourself. So use things like Caboodle, Seneca, knowledge checkers to quickly test your own knowledge, and you might wish to do this from your own cue cards. The third step is to practice examination questions. So use exam prep books, homework books, supervised study books, additional workbooks to answer exam questions and mark your own work, and you might wish to download your own exam past papers to do this. So the three steps are learn the key facts, testing yourself and practicing examination style questions. Now in this revision session we'll have three different types of questions. The first type of question is the general check question, designed to probe your understanding of the key concepts of the topic. The second part is the checkpoint. These are more challenging questions designed to place your knowledge and understanding of the topics into different contexts and applications. The third type of question is assessment point questions. Now these are past paper examination questions which mimic the types of questions found in public examinations. So let's have a look at thermal physics. So the first question say, describe a liquid in terms of its arrangements of particles, the bonding between them and their motion. Then use the kinetic model of matter to explain the following. If you leave a pan of water on the hob for a long time, it will not all boil away as soon as the temperature reaches 100 degrees Celsius. It takes less time to melt 1 kilogram block of ice at 0 degrees Celsius than to boil away 1 kilogram of water at 100 degrees Celsius, and then when a dog overheats, it pants. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, you know that the bonding and links of particles are that for a liquid, bonds are relatively strong. They're stronger than a gas, but weaker than a solid, and the molecules are free to move through the body of the liquid. Now in the second one, 2.1, it's the idea that the energy has to be supplied to convert the liquid into a vapour, which takes time to do this. It takes time to break away those bonds. In the third one, when ice is converted into liquid water, only a few intermolecular bonds will be broken to go from a solid to a liquid, whilst when you go from a liquid to a gas to a vapour, all the molecules are completely separated, all the intermolecular bonds are broken. That requires more energy. And then finally, a dog doesn't actually sweat through his skin like humans do. Instead, they sweat from their tongues. The sweat then evaporates and cools the dog. Now, panting blows air across the tongue, which will increase the rate of evaporation. The next question says, a solid is heated until it melts. The heating continues until the liquid metal boils. Compare the similarities and differences between melting and boiling for a metal. Your answers refer to the energy of the metal, the separation between the atoms of a metal, and the forces between the atoms of a metal. So pause the video now, then unpause the video when you want to go through your answer. Right. What's similar about the solid and the liquid metal? Well, the first thing is in similarities, energy has to be supplied in both melting and boiling. So it means that both melting and boiling will increase the overall internal energy of the atoms in the metal. Now, in terms of the melting and boiling, it's a change of state. So we know during a change of state, there'll be no change in temperature because there's no change in the kinetic energy store of the substance, only the potential energy store. Now, what are the differences? Now, boiling results in a larger separation between the atoms. So in boiling, the particles are separated so far apart that almost no force will exist between the atoms, okay, whilst in melting, the atoms are separated sufficiently to slide over each other, but not completely. So we can say that in boiling, the atoms have become pretty much independent of each other and all the intermolecular forces of attraction or intermolecular bonds have been removed. That's not the case when they're melting. Now, we also know that boiling occurs at a higher temperature. Temperature is proportional to the kinetic energy store of the object, so therefore the atoms will be moving faster or have a greater kinetic energy during boiling than there would be during melting. And then we also know, as stated previously, more energy is needed to be separating the molecules in boiling compared to when it would be in melting. The next question says, use the first law of thermodynamics to answer the following. A gas is heated by supplying with 250 kilojoules of energy. At the same time, it is compressed so that 500 kilojoules of work is done on the gas. Calculate the change in internal energy of the gas. Then the same gas is heated as before with 250 kilojoules of energy. This time the gas is allowed to expand so that it does 200 kilojoules of work on its surroundings. Calculate the change in the internal energy of the gas. So pause the video now, then unpause the video when you want to go through your answer. Right, what do we know? Well, we know that from the first law of thermodynamics, the change in internal energy is equal to the energy supplied by heating the object plus the energy supplied by doing work on the object as well. Now, you do work on the gas when it is compressed. You do not do work is done by the gas when it's expanding. So we know that there's 250 kilojoules supplied by heating. There's 500 kilojoules supplied when it's compressing the gas. So overall, it's plus 750 kilojoules. So work is going into the gas. In the second one, again, change in internal energy is equal to the energy supplied by the heating plus the energy supplied by doing work on the gas. Now we know here that the gas is expanding, so therefore it's 200 kilojoules out of the gas. So therefore it is minus 200. So it is plus 250 minus 200, so therefore it's 50 kilojoules. The next question says, convert each of the following temperatures from the Celsius scale to the thermodynamics scale, which is the Kelvin scale. So 0 degrees Celsius, 20 degrees Celsius, 120 degrees Celsius, 500 degrees Celsius, minus 23 degrees Celsius, and minus 200 degrees Celsius. Then convert the following temperatures from the thermodynamic or Kelvin scale to the Celsius scale. 0 Kelvin, 20 Kelvin, 100 Kelvin, 300 Kelvin, 373 Kelvin, and 500 Kelvin. And then give one word for each of the following. Add in a scale to a thermometer. All the temperatures from lowest to highest which a thermometer can measure. The extent to which equal rise in temperature give equal changes in a thermometer's output. And then how big a change in output is produced by a given temperature. So pause the video now, then unpause the video when you want to go through your answer. Right, we need to know the difference between the temperature in Kelvin and the temperature in degrees Celsius. So temperature in Kelvin is equal to the temperature in degrees Celsius plus 273.15. So we get 273, 293, 393, 773, 250 and 73 Kelvin. It's the other way around for the next one. So the temperature in degrees Celsius is the temperature in Kelvin minus 273.15. So it's minus 273 degrees Celsius, minus 253 degrees Celsius, minus 173 degrees Celsius, plus 27 degrees Celsius, plus 100 degrees Celsius, and plus 227 degrees Celsius. Adding a scale to a measuring device is called calibration. The values from highest to lowest a measuring device can measure is the range. The extent to which the equal change in temperature given equal change in the output is called linearity, and then how big a change in output is produced by a given change in temperature is the sensitivity of the device. The next question says, a block of paraffin wax was heated gently at a steady rate. The heating was continued after the wax had completely melted. The graph shows how the material's temperature varied during the experiment. For each section of the graph, describe the state of the material. For each section, explain whether the material's internal energy was increasing, decreasing, or remaining the same. Then consider the two sloping sections of the graph. State whether the material's specific heat capacity is greater when it is a solid or when it is a liquid. Justify your answer. So pause the video now, unpause the video and you want to go through your answer. Right, so AB is going to be a solid, BC is when it's melted, so it's a solid and a liquid. And then CD is there when it's fully become a liquid. Now in each part, AB, BC and CD, you are putting energy into the substance by heating it up, so the internal energy is going up in all three sections. Now in the next one, in two sloping sections, the specific heat capacity is greater when it's a solid, because the specific heat capacity is the energy needed to change the temperature by 1 degree Celsius when you have 1 kilogram. Now the gradient is greater when it's a liquid, so it takes less time to raise the temperature by the same amount when you transfer the same amount of energy, so therefore the less energy is needed. The next question says, calculate the energy which must be supplied to raise the temperature of 5 kilograms of water from 20 degrees to 100 degrees. Then which requires more energy, heating a 2 kilogram block of lead by 30 Kelvin or heating a 4 kilogram block of copper by 5 Kelvin? Then a well-insulated 1.2 kilogram block of iron is heated using a 50 watt heater for 4 minutes. The temperature of the block rises from 22 degrees Celsius to 45 degrees Celsius. Find the experimental value for the specific heat capacity of iron. So pause the video now, then unpause the video when you want to go through your answer. Right, we know that to work out the energy supplied when you've got a change in temperature, it's E equals MC, change in temperature. So you can do for each one, and there you get 1.7 megajoules when you pop in all the values. The next one, here again, you work out each one with E equals MC, change in temperature. So for the lead, you'll get 7.56 kilojoules. For the copper, you get 7.60 kilojoules. So the copper block requires more energy. Now, in this instance, it's a bit harder because we haven't got energy, but we have got power and time. So energy is power times time, where time is given in seconds, so therefore our energy will be 12 kilojoules. We can then say C equals E over M change in temperature, so therefore when we work it all through, we get about 435 or 440 joules per kilogram per Kelvin. The next question says, at higher temperatures, the graph shown deviates increasingly from a straight line. Suggest an explanation for this. Then in measurements of the specific capacity of a metal, energy losses to the surroundings are a source of error. Is this a systematic error or a random error? And justify your answer. Then, in an experiment to measure the specific heat capacity of water, a student used an electrical heater to heat up some water. His results are shown below. Calculate a value for the heat capacity of water. Comment on any likely sources of error. So pause the video now, then unpause the video when you want to go through your answer. Right, you've got to remember at higher temperatures that the object will be a greater radiator of energy. So therefore the rate of energy lost to the surroundings is greater, so the temperature rise of the substance will be lower. Now, energy loss to the surroundings is a systematic error because it can be theoretically removed by perfect insulation, which is what we define systematic error to be, an error that can be removed from the experiment by taking away the value of the error. Now in this next one, the first thing we can do is work out the mass of the water by doing the mass of the beaker minus, so it takes away from the mass of the beaker and the water, so we therefore get 0.522 when you work through your answer of grams, which they convert into kilograms afterwards. We can then say power is P equals VI because we've got current, we've got potential difference, so it's 44.5 watts. In 30 minutes, you can work out the energy supply by doing E equals power times by time. Convert our 13 minutes into seconds, so we get 34.7 kilojoules. We can work out our change in temperature. We can then say C equals E over M times by change in temperature. We then work it all through and we get 5,700 joules per kilogram per Kelvin. Now the biggest source of error, as mentioned before, will be the energy lost due to the surroundings. Now this could also include the energy being given to the beaker itself, so therefore we can reduce that by insulating the entire substance. The next question says, a student measured the temperature of some oil in a beaker. The temperature of the oil is 20 degrees Celsius. Give this temperature in Kelvin. Then the student heats 600 grams of oil using an immersion heater. The temperature of the oil increases from 300 Kelvin to 350 Kelvin. Show that the minimum amount of energy supplied to the oil is approximately 63,000 joules. The specific heat capacity of the oil is 2,090 joules per kilogram per Kelvin. So pause the video now, then unpause the video when you want to go through your answer. Right, so we can convert from degrees Celsius into Kelvin by adding 273.15, that's 293.15 Kelvin. Here we know E equals MC triangle T. We convert our grams into kilograms. We then work out our change in temperature to be 50. We pop in all the values and we get 62,700 joules. The next question says, describe the changes to the kinetic energy, the potential energy, and the total internal energy of the molecules of a block of ice as it melts at 0 degrees Celsius and as the temperature of the water rises from 0 degrees Celsius to room temperature. Then explain in terms of kinetic energy why the temperature of a stone increases when it falls from a cliff and lands on a beach. Explain why the barrel of a bicycle pump gets very hot as it's used to pump up a bicycle tyre. And then the zeroth law of thermodynamics states that if the temperature of a body A is equal to the temperature of body B, and the temperature of body B is the same as body C, then the temperature of body C equals that of the temperature of body A. Explain in terms of energy flow why the concept of temperature will be meaningless if this law was not obeyed. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, because we're changing state, the kinetic energy remains constant, the potential energy will increase because we are changing state by heating it up, so therefore the overall internal energy increases. In this next one, the kinetic energy will increase as the temperature increases, the potential energy remains constant, so therefore the overall internal energy will increase. Now in this next one, just before the stone hits the ground, it has kinetic energy. So all the molecules moving together in the same direction. When it hits the ground, the unidirectional movement of the molecules is converted into the movement of individual molecules in random direction. So therefore the kinetic energy from movement in random directions is the internal energy, and therefore the temperature will rise. In the next one, the air is being compressed, so work is being done on it. So from the first law of thermodynamics, the change in the internal energy of a body is equal to the energy supplied by heating plus the energy supplied by doing work. So therefore there's no energy supplied by heating, but work is being done by compressing that gas, by compressing the air. Now in this last one, if two bodies are the same temperature, no energy flow will happen from one body to another. So therefore if no energy flows from A to B and none flows from B to C, but if energy did flow from C to B, it would mean that A and B were the same temperature, and A and C are the same temperature, but C will be hotter than B, which is clearly not correct, which is a fundamental law in thermodynamics. The next question says, the specific latent heat of vaporization of water is 2.26 megajoules per kilogram. Calculate the energy needed to change 2 grams of water into steam at 100 degrees Celsius. The specific latent heat of fusion of water is 330 kilojoules per kilogram. Calculate the energy needed to change 2 grams of ice into water at 0 degrees Celsius. Suggest why the answer is much smaller than the amount calculated in 1.1. Then a sample of alcohol is heated with a 40 watt heater until it boils. As it boils, the mass of liquid decreases at a rate of 2.25 grams per minute. Assuming that 80% of the energy supplied by the heater is transferred to the alcohol, estimate the specific latent heat of vaporization of the alcohol, given your answer in kilojoules per kilogram. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one we know E equals ml, that's the equation for latent heat, so therefore we can pop in the values. Remember to convert grams into kilograms, convert the megajoules per kilogram into joules per kilogram, so therefore it's 4,520 joules. In this next question, E equals ml again, convert our grams into kilograms and our kilojoules per kilogram into joules per kilogram. So when you multiply them together, we get 660 joules. Now when a solid melts, only about 1 bond per atom or molecule is broken in the melting process. But in boiling, all of the bonds are broken, so it needs more energy to do this. Now in this next question, we know that the rate of loss of mass is 2.25 grams per minute, so we can work that into seconds and say it's therefore 3.75 times 10 to the minus 5 kilograms per second. Now the energy supplied to the alcohol is 80% of the energy supplied by the heater, so 40 times by 0.8 is 32 watts, so therefore the latent heat L is going to be equal to E over M, or the rate of energy supplied divided by the rate of mass loss, so therefore it's the power over the rate of mass loss, so we can pop those values in and we get 850 kilojoules per kilogram. The next question says, a cylinder contains 0.80 decimeters cubed of nitrogen gas at a pressure of 1.2 atmospheres. A piston slowly compresses the gas to a pressure of 6 atmospheres. The temperature remains constant. Calculate the final volume of the gas. Then a balloon contains 0.04 meters cubed of air at a pressure of 120 kilopascals. Calculate the pressure required to reduce its volume to 0.025 meters cubed at a constant temperature. So pause the video now, then unpause the video and you want to go through your answer. Right, here we've got to remember that Boyle's law, that P1V1 equals P2V2. You don't need to change units because it's a ratio, so you pop in the values, so you get 0.16 decimeters cubed. Do the same for the next one. We can work it all through. Here we can then change it into pascals just to make it easier and work out our value. So we work it through and we get 1.9 times 10 to the 5 pascals. The next question says a sealed container contains 60 moles of gas at a temperature of 250 Kelvin and a pressure of 60,000 pascals. Calculate the volume of the container. State the effect on the pressure of a fixed mass of gas at constant temperature if the volume of the gas is doubled or reduced to a third of its original value. Then a fixed mass and volume of gas initially at a temperature of 20 degrees Celsius and a pressure of 300 kilopascals is heated to 100 degrees Celsius. Calculate the change in pressure. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we've got moles, we've got temperature in Kelvin, we've got pressure. So we can say PV equals nRT, the ideal gas equation. So V equals nRT over P. R is the molar gas constant given to you on your equation sheet. Pop in all the values, 2.1 meters cubed. We can say here, if you remember for Boyle's law, that P and V are inversely proportional to each other. So therefore, if the volume is doubled, the pressure will half. And if the volume is reduced to a third, well then P would increase by 3 or would triple. Now in this next one, we know from the second law, from Charles's gas law, that P over T is a constant. So we can work out what that constant is from the initial values given. So it's 300,000 over 293. We converted our temperature into Kelvin and our pressure into pascals, so we get 1020. So therefore afterwards we can say pressure is that constant times by the new temperature, again in Kelvin. So therefore we work out the new pressure is 401,000 pascals, and it asks for the change in pressure, so find the difference between that and the starting pressure of 300,000, so it's 101,000 pascals. The next question says, Figure 4 shows an example of a Carnot cycle engine. The cylinder contains a fixed mass of gas. The piston moves in the direction as shown. Explain what happens to the internal energy of the gas, refer to the motion of the gas molecules and the gas temperature. A cylinder contains some gas at a temperature of 400 Kelvin. The pressure of the gas in the cylinder is 201,400 pascals. The cylinder and the gas inside the cylinder cool to 293 Kelvin with no change in volume. Calculate the pressure of the gas when its temperature is 293 Kelvin. So pause the video now, then unpause the video when you want to go through your answer. Right, we know that the internal energy of the gas will increase. Why is that? Well, the gas is being compressed, so therefore work must be being done onto the gas. So therefore energy is being placed into the gas. This will cause the temperature to increase because in theory there's no potential energy in the gas, because therefore the molecules will have a high kinetic energy. In this next one, again we use P1V1 equals P2V2. We work it all through, remember popping all the values in, and we get 148,000 pascals. The next question says, consider a smoke particle of mass m and speed v. It is constantly buffeted by air molecules. The mass of a single air molecule is m and its speed is v. It is reasonable to assume that on average the smoke particle will have a kinetic energy approximately equal to the kinetic energy of a single air molecule. Show that big M is much greater than small m, and it follows that the air molecules must be moving much faster than the smoke grain. Then if equal numbers of air molecules hit a smoke particle from all directions, the smoke particle does not move. State 3 ways in which the random movement of molecules of air causes the smoke particle to move. Describe and explain what you would see through a microscope observing Brownian motion when the temperature increases. Then an oxygen molecule is moving around inside a spherical container of diameter 0.10 meters. The molecule speed is 400 meters per second. Estimate the number of times each second the molecule collides with the container's walls. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, the time taken to cross the diameter of the container once is distance over time, which you can work through with the values roughly to be about 2.5 times 10 to the minus 4 seconds. So if you assume a molecule speed is constant and therefore each collision is including like that, okay, well therefore you can say the number of collisions is 1 over time, so it's 1 over 2.5 times 10 to the minus 4, so it's about 400 collisions every second. Now, it's different because the different number of molecules hit one side than the other. The number of molecules striking any area per second will vary. The speed of the molecules hitting will vary, and the angle that the molecules hit the smoke detector will also vary. The next one, you'll see with Brownian motion, the smoke particles will move faster and more erratically because at a higher temperature, the molecules of air will be moving faster because temperature links to the kinetic energy of the molecule. So therefore, the impact will cause a greater change in the momentum of the smoke particle. Okay, and then finally, okay, as we said before, the answer is going to be 400 times per second. Now the next question says, state and explain in terms of the kinetic model what happens to the pressure inside a tyre when more molecules at the same temperature are pumped into the tyre. Then explain using the kinetic model why a can containing air may explode if the temperature rises. So pause the video now, then unpause the video when you want to go through your answer. Right, remember that pressure is caused by the change in momentum that the particles have on the side of a container. So the pressure increases because more particles are hitting a unit area of the tyre every single second. The frequency of collisions has gone up. So the molecules have the same speed because they've got the same temperature, and temperature links to kinetic energy. So each collision will cause the same impulse or change in momentum. Now since more molecules hit per second, the rate of change of momentum, which is the force, will increase, which increases the pressure. Now in the next one, at higher temperatures, the molecules have higher internal energy and therefore move faster because the only internal energy they have is kinetic energy. So the number of collisions per second will increase, and the change in momentum of each collision will also increase because they're hitting harder. So for both these reasons, the rate of change of momentum of the molecules increases. Now the force on the wall is equal and opposite to the rate of change of the momentum of the molecules. So as the force increases, the pressure inside the can will also increase, which may cause it to explode. In the next question it says, check that the units on the left hand side of the equation, P equals a third, Nm over V times by C squared, are the same as those on the right hand side. Then the quantity Nm is the total mass of the molecules of the gas. So the mass of the gas. At room temperature, the density of air is about 1.29 kilograms per meters cubed at a pressure of 10 to the 5 pascals. Use these figures to deduce the value of c squared for air molecules at room temperature, and then find a typical value for the speed of a molecule in air by calculating the root of c squared. How does this compare with the speed of sound in air? So pause the video now, then unpause the video when you want to go through your answer. Right, let's look at some dimensional analysis. So the units of pressure is P equals F over A, so therefore it's MA over A, which we can therefore say is kg m s to the minus 2 over m squared. So therefore the overall units of pressure are kg m to the minus 1 s to the minus 2. Whilst on the right hand side, we can say it's Nm times by c squared over V, so therefore it's going to be kilograms, because n is just a number, so it'll have no values. So it'll be kg, there'll be ms to the minus 1 squared, because it's going to be speed squared, divided by the volume, which is meters cubed, which goes to be kg m to the minus 1 s to the minus 2, which is the same units on each side. In this next one, we can rearrange the equation to say P equals Nm times by c squared over 3V. So therefore c squared is equal to 3pV over Nm. Pop in all the values, we can work it through. Now remember, density is mass over volume, so therefore you can link it to be divided by the density, because it's going to be m over v. So therefore it's 3 times 10 to the 5 times by 1 over 1.29, 2.3 times 10 to the 5 meters squared seconds to the minus 2. Then we can work out our answer by square rooting this value to be 480 meters per second, which is about 50% greater than the speed of sound in air, 330 meters per second. The next question says the Boltzmann constant K is equal to R over Na. From the values of R and Na, show that K has a value of 1.38 times 10 to the minus 23 joules per Kelvin. Then write down an equation linking the Boltzmann constant, the thermodynamic temperature, and the average kinetic energy of a molecule. Calculate the mean kinetic energy of atoms in an ideal gas at 27 degrees Celsius. The atoms in a gas have a mean kinetic energy equal to 5 times 10 to the minus 21 joules. Calculate the temperature of the gas in Kelvin and then in degrees Celsius, and then show that if the mean speed of the molecules in an ideal gas is doubled, well then the thermodynamic or Kelvin absolute temperature in Kelvin of a gas is increased by a factor of 4. So pause the video now, then unpause the video when you want to go through your answer. Right, we can work out the Boltzmann constant because K is equal to R over Na. You're given R, you're given Na on the equation sheet, so you get 1.38 times 10 to the minus 23 joules per Kelvin. The next one we know from the equation sheet that the kinetic energy of one molecule is 3 over 2 kT, where T is in Kelvin. So therefore we work it through by saying, well, 3 over 2 kT or 3 over 2 RT over Na, pop in all the values, convert the temperature into Kelvin, so we get 300, and then we work it through to be 6.2 times 10 to the minus 21 joules. In this next one again, we can say, well, kinetic energy is equal to 3 over 2 kT or is equal to a half mc squared, so half mv squared. Pop in all the values, remember to make T the subject, which is 242 Kelvin or minus 31 degrees Celsius. Then we can see that temperature from the previous equation is going to be proportional to the average speed squared. So therefore, if the speed doubles, well then the temperature will increase by a factor of 2 squared, which is 4. The next question says, a fixed mass of gas expands to twice its original volume at a constant temperature. How do the following change? The pressure of the gas and the mean kinetic energy of the gas molecules. Air consists of oxygen, molar mass 32 grams per mole, and nitrogen, molar mass 28 grams per mole. Calculate the mean kinetic energy of these molecules in air at 20 degrees, then estimate the typical speed for each type of molecule, and then show that the change in internal energy of 1 mole of an ideal gas per unit change in temperature is always constant, and what is this constant going to be? So pause the video now, then unpause the video when you want to go through your answer. Right, we can see that, like we said before, PV equals to a constant. So therefore, if we can work it through to say that if it's now twice its original volume, well, therefore the pressure will half. Now the kinetic energy will remain the same because E equals 3 over 2 kT. K and T are constant, so therefore the kinetic energy will be constant. We can work out the kinetic energy for each one by doing 3 over 2 kT, or we could be doing a half mv squared. Now m is the mass of one molecule, so you can work that through by doing, well, the molar mass is divided by Avogadro's constant is going to therefore give you the mass of one molecule, because the molar mass is the mass of one mole. The Avogadro's constant is the number of molecules in 1 mole, so therefore you can work it through that way. So when you work it all through, make V the subject to work out the average speed of the molecules. Oxygen comes out to be 480 meters per second, and nitrogen comes out to be 510 meters per second. Now, like we said before, we can say that the internal energy is going to be the kinetic energy store, because in a gas there's no potential energy in that gas, so it's only kinetic energy being the internal energy store. So therefore it's the kinetic energy of one molecule, 3 over 2 kT, times by the number of molecules in that gas, which is 1 mole, so therefore it is Avogadro's constant. We know that, therefore we can say that Na, okay, then in that point divided by K at that point, so times by K will equal R, so therefore it's 3 over 2 RT, so therefore the change per Kelvin is 3 over 2R. The next question says, describe what happens to the absolute temperature of a gas if the RMS speed of the particles in the gas firstly increases, then doubles, then increases by a factor of 5. Then the gas canister has a volume of 0.50 meters cubed. The pressure inside the canister is 450 kilopascals and the temperature is 18 degrees Celsius. Calculate the number of particles of the gas and the number of moles inside the canister. Then explain why doubling the temperature of a real gas does not double the internal energy. So pause the video now, then unpause the video when you want to go through your answer. Right, well, firstly, we know that temperature links into speed because they're proportional to each other. Okay, so therefore as the temperature increases, well, therefore the speed will also increase. Okay, next one, we know that temperature is actually proportional. Okay, so it links to the speed squared. So if the speed doubles, well then the kinetic energy will quadruple as the temperature will also quadruple. And then once again, if the speed increases by a factor of 5, the kinetic energy and the temperature will increase by a factor of 25 because it's proportional to 5 squared. Now in the next question, we can work out the value here by saying PV equals big N kT. That's another ideal gas equation. So N equals PV over kT. Remember, P is in pascals, not kilopascals, so you can pop in all those values, convert 18 degrees Celsius into Kelvin, so you get 5.6 times 10 to the 25 particles. Divide that then by Avogadro's constant, the number of particles in 1 mole, to work out the number of moles, so you get 93.1 moles. Now in the last question, double the temperature of a gas in the real world doesn't actually double the internal energy. It will double the kinetic energy of the atoms in the gas, mass, but the atoms and molecules in a real gas will also have potential energies, which we don't assume in an ideal gas. So in a real gas, the internal energy is equal to the sum of the kinetic and the potential energies of the atoms within the gas. So doubling the kinetic energy won't equal the doubling the internal energy, because there's potential energy there as well. The next question says, an oxygen molecule has a mass of 5.3 times 10 to the minus 26 kilograms. Calculate the RMS speed of an oxygen molecule at room temperature. Then compare the kinetic energy and RMS speed of room temperature of a helium atom of mass 6.6 times 10 to the minus 27 kilograms with the answer to the previous question. So pause the video now, then unpause the video when you want to go through your answer. Right, we can say, well, a half mv squared or half mc squared is equal to 3 over 2 kt. Rearrange it, make the speed the subject, pop in all the values, change the temperature into Kelvin, so therefore we get 480 meters per second. Now we should know that kinetic energy is 3 over 2 kt, so because they're at the same temperature, room temperature, they'll have the same kinetic energy, but the speed of the helium atom will be greater because the oxygen molecule has 8 times as much mass as the helium one does. So therefore, to have the same kinetic energy, the helium must be travelling at 2.8 times, or square root 8, because a half mv squared, faster, so they link in like that. The next question says, wax is heated until the temperature is melted above the melt point of the wax. The hot wax is poured into a bowl and allowed to cool. The graph shows how the temperature of the wax varies with time as it cools. Describe how the internal energy of the wax changes as the wax cools. Usually refer to the energy of the wax molecules as the liquid cools and becomes a solid, and the solid wax cools. Times x and y have been included to help refer to the graph. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, the internal energy of the wax decreases during cooling because energy is leaving the substance. So the internal energy is the sum of the potential and the kinetic energy of the molecules. As the temperature decreases, then the kinetic energy store of the molecules will decrease. So between times x and y, as it's solidifying, the potential energy store decreases because it's changing state. Between times x and y, the temperature is constant because there's no change in the kinetic energy store. At time y, the wax is finished solidifying and the temperature then starts to drop. The next question says, a 500 watt kettle contains 300 grams of water at 20 degrees Celsius. Calculate the minimum time it would take to raise the temperature of the water to boiling point. Then the kettle is allowed to boil for 2 minutes. Calculate the mass of the water that remains in the kettle, stating any assumptions that you make. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can see E equals MC triangle T, or change in temperature, because there's a change in temperature here. Convert our grams into kilograms, and we work it through to be equal to 100,320 joules. Time is energy over power. We know it takes 500 seconds, because we work in 500 watts there. So we get our answer out to be 201 seconds. Now we're assuming no energy goes into heating the element or the kettle or is being lost to the surroundings. Now in this next one, again, we say E equals power times by time, so it's 500 times by 120. Minutes go into seconds, so we get 60,000 joules. The mass of water boiled away, because it's a change in energy, a change in state, is going to be E over the specific latent heat. So it's 60,000 over 2.26 times 10 to the 6, which is 0.027 kilograms. So therefore that's 27 grams. So therefore the mass left over is going to be 300 grams, the starting mass, which is told you in the previous part of the question, minus 27. So it's about 270 grams. Now we're assuming here that no energy is lost to the surroundings and all the vapor will escape the kettle. The next question says, explain what is meant by the specific heat capacity of a substance. Now the figure shows the apparatus used to measure the specific heat capacity of a copper block of mass 850 grams. The block is initially at 12 degrees Celsius. The heater is switched on and the time taken for the temperature to rise to 30 degrees is recorded. The block is cooled to the original temperature and the potential difference across the heater is increased and the experiment is repeated. The results are shown below. Explain why a thermocouple thermometer is suitable for this experiment. Explain why the experiment is repeated using a different power input and calculate the specific heat capacity of the copper. So pause the video now, then unpause the video when you want to go through your answer. Right, so the first one's a definition. So it is the energy required to raise the temperature of 1 kilogram or a unit mass of a substance by 1 degree Celsius. Now a thermocouple thermometer is used because it has a very small heat capacity and it can quickly act and will quickly record the temperature. The next one, we will use different power inputs to allow for energy losses to the surroundings. So to work out the heat capacity, you'll do the input of the energy, which is 40 times by 190, so 7,600 joules. The experiment one is the energy input is MC triangle T plus the energy losses. So you can work that through to be 7,600 equals 15.3 C plus Q1. Same for experiment 2, and you get 6,840 equals 15.3 plus Q2. You can then subtract the equations 1 and 2 to get 7,600 minus 6,840 equals Q1 minus Q2. We can then sub that into the previous equations, and therefore we can work out Q1 to be 1,900 joules. So therefore when you pop it into the equation for 1, we will say 7,600 equals 15.3 C plus 1,900, we get 372 joules per kilogram per degree Celsius. The next question says, an electric shower runs at 230 volts and 46 amps. In the summer, it increases the water temperature from 22 degrees Celsius to 39 degrees Celsius. Calculate the thermal energy used to increase the temperature of 1 kilogram of the water. Now, the heat capacity of the water is 4,200 joules per kilogram per Kelvin. Calculate the time it will take the heater to deliver this amount of thermal energy. In winter, the inlet water temperature drops to 5 degrees Celsius, but the final temperature remains at 39 degrees Celsius. State and explain the change to the water flow rate for this shower in winter compared to summer. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, E equals MC triangle T, or change in temperature. So it's 4,200 times by 1 times by 17, 71.4 kilojoules. Now we can say T equals this energy, okay, divided by IV, or the power. So therefore it's 71.4 times 10 to the 3 over the power, which is 230 times by 46, is 6.75 seconds. And we can say in this next one, the change in temperature is doubled, so therefore the flow rate, or the change in mass per time, is going to have to halve to keep that constant value for C, because we can see that C is going to equal to be delta E over MC triangle T, or delta phi, so therefore it's going to have to halve for when the change in temperature is doubled. The next question says, cocoa powder, milk and hot water are mixed together to produce a hot chocolate. The mass of the drink is 275 grams and its initial temperature is 71.5 degrees Celsius. The ice at 0.0 degrees Celsius is added to the drink to reduce its temperature. Research indicates that the maximum serving temperature of any hot drink should be 58.0 degrees Celsius. Deduce whether 4 grams of ice would be enough to bring the temperature below 58.0 degrees Celsius. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question we can say that the energy transfer from the hot liquid is the energy transferred to the ice plus the energy transferred to the cold water. So we can say that E is going to equal MC, change in temperature, so 0.275 times by 3,750 times by 71.5 minus 58, which will equal those two other energies, so M times by L plus by M times by C times by change in temperature. So we can work that through, and we've got M coming out as a constant term. So as you can see here, M is going to equal 1.39 times 10 to the 4 over 5.77 times 10 to the 5, which equals about 24 grams. So adding 4 grams wouldn't bring the temperature below the ideal serving temperature. You would in fact need 24 grams for this to work. The next question says, lead shot contains a small lead spheres. Originally, lead shot was made by dripping molten lead through copper sieve from the top of a shot tower. The lead cooled as it fell before landing in the water and producing solid lead spheres. Figure 1 shows a shot tower, and Figure 2 shows the process of a lead shot in the shot tower. Now, to avoid producing steam, the temperature of the lead was below 100 degrees Celsius as it reached the cold water. As the lead sphere falls through the distance of 41.5 meters, so it takes 3 seconds for the lead sphere to fall this distance, assuming that resistive forces are negligible. The lead sphere has a radius of 1.2 millimeters. As it falls, it cools from 615 to 370 Kelvin. The molten lead solidifies at 601 Kelvin. Calculate the mean rate at which the energy is transferred from the lead sphere to the surroundings. You should assume that the sphere heat capacity of liquid lead and the solid lead are the same. So pause the video now, then unpause the video when you want to go through your answer. Right, we can just use suvat in this question because it's going to be constant acceleration. So s equals ut plus a half at squared. Remember, a is minus 9.81 and s is minus 41.5. So therefore t will equal 2.91 seconds. In this next one, we work out what the volume is going to be by doing 4 over 3 pi r cubed. So we get our volume out. We can then say the mass is the density times by the volume. So we get our mass to be 8.18 times 10 to the minus 5 kilograms. We can then say, well, what's the energy change going to be when it changes temperature? Well, we do E equals mc change in temperature, pop in all those values, and you get 2.61 joules. We can then look at E equals ml as it changes state, as it solidifies, by doing mass times by the latent heat capacity, which is 2.02 joules. So add the two together, that's the energy change, divided by the time will give you the power, so you get 1.60 watts. The next question says, a student learns that the energy required to heat water for a bath can be 10 times the energy required to heat water for a shower. The student uses the shower for 9 minutes and the water comes out of the shower at 38 degrees at a flow rate of 1.8 times 10 to the minus 5 meters cubed per second. The student usually fills the bath with 160 kilograms of water at 32 degrees Celsius. Deduce whether the bath uses 10 times more energy than the shower. So pause the video now, then unpause the video when you want to go through your answer. Right, so what we can do is work out the energy change for each one. So in the let's have a look at the bath first. So E equals mc triangle T, or change in temperature. So you can pop in all the values and then we pop out, we get 1.14 times 10 to the 7 joules. Now look for the shower. What's the mass going to be? Well, in 1 second the mass is going to be the flow rate for that 1 second. So it's going to be 1 times 10 to the 3 kilograms per meters cubed times by 1.8 times 10 to the minus 5, because we're saying mass is density times by volume. So therefore it's going to be 0.018 kilograms. So therefore we can then work out what it's going to be for 60 seconds. So say they're in the shower for 9 minutes, so do 60 seconds times by 9, so it's 0.018 times by 9 times by 60 is 9.72 kilograms. So therefore E equals mc change in temperature for this one, and we'll say it's 38 to 15, so there's your difference there. So it's 9.34 times 10 to the 5. Find the ratio of the two, and it's 12.2 times, so actually it is more than 10 times. The next question says, ice cubes can be made in an ice cube tray. One type of ice cube is shown. Each compartment in the ice cube tray has dimensions of 2.5 centimeters by 2.5 centimeters by 3.5 centimeters. Show that the mass of the water needed to fill one compartment is about 0.02 kilograms. Then all 6 compartments in the ice cube tray are filled with the water to a depth of 3.5 centimeters. The ice cube tray is placed in a freezer. The initial temperature of the water is 22.5 degrees Celsius. It takes 12 minutes for all the water to become ice at 0 degrees Celsius. The manufacturer of the freezer states that the freezer can transfer energy at a rate of 110 watts. Evaluate whether energy is transferred from the water in the tray at a rate of 110 watts. So pause the video now, then unpause the video when you want to go through your answer. Right, so we know density is mass over volume, so therefore volume is going to work out to be the mass, okay, divided by, so you can work out what the volume is going to be by doing 2.5 times 10 to the minus 2 times by 2.5 times 10 to the minus 2 times by 3.5 times 10 to the minus 2, turning centimeters into meters, so we get 2.19 times 10 to the minus 5. We can therefore say that the mass is going to be working it through to be the density times by the volume. So we've got the density, we've got the volume, multiply them together, we get 0.0219 kilograms. In this next one, we can say that the change in energy is mc change in temperature. Pop it all through. Now again, remember, it is going to be 22.5 because it starts at 0 and goes to 20, or starts at 22.5 and goes to 0. Pop in all the values. Remember, there's 6 of them when you're working out the mass, so it's 1.24 times 10 to the 4 joules. We can therefore say E equals ml because it's also freezing and change in state. Remember, the mass is 6 of them. Then multiply by the latent heat of fusion, and we get 4.41 times 10 to the 4. Add the two together to get the total energy change, divided by the time, which is going to be in seconds, not minutes. So we work it through to be 78.5 watts. So therefore, it is not at a rate of 110 watts. The next question says, a cylinder holds 140 decimeters cubed of nitrogen at room temperature and pressure. Moving slowly so that there is no change in temperature, a piston is pushed to reduce the volume of nitrogen to 42 decimeters cubed. Calculate the pressure of the nitrogen after compression. Explain the effect on the temperature and pressure of the nitrogen if the piston was pushed in very quickly. Then the atmospheric pressure is 100 kilopascals, equivalent to the pressure exerted by a column of water 10 meters high. A bowl of oxygen of volume 0.42 centimeters cubed is released by a water plant at a depth of 25 meters. Calculate the volume of the bubble when it reaches the surface. State any assumptions that you make. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one again, we're using Boyle's law. So P1V1 equals P2V2. So P2 is going to be equal to 3.4 times 10 to the 5 pascals. Remember, you don't have to change the units because it's just a ratio. Now we know that PV equals a constant, so therefore, what else do we know about that? That in the other way around, we can link in pressure and temperature as well. So when the temperature of the gas increases, that will cause the pressure to be higher than the previous question. Again, we can also now use Boyle's law again to work out what V2 is going to be. Again, you don't need to change units as long as it's in the same unit, so therefore the answer is going to be 1.5 centimeters cubed. Again, this assumes that the temperature at a 25 meter depth is equal to the temperature of the surface of the water for it to work through, because we can only work if it's a constant temperature, so we get 1.5 centimeters cubed. The next question says, this question is about an investigation into the relationship between pressure and volume of a gas. This is often referred to as Boyle's law. A student sets up the apparatus as shown in the picture. Identify a variables needs to be controlled in the investigation. Then before setting up the apparatus, the student took measurements of the vernier calipers of the internal diameter of the tube containing the gas. The student created a dot plot of the cross-sectional area as shown. Taking into consideration any outliers, calculate the value for the mean and percentage uncertainty of the cross-sectional area of the tube, given your answers to the appropriate number of significant figures. So pause the video now, then unpause the video when you want to go through your answer. Right, you've got to know that for Boyle's law, it only works if the temperature is constant, so that's the control. Now, if you look at the information given in the previous question, you can identify there's an outlier or anomalous result, it's 79. So therefore, you can calculate the mean correctly. So the range, you work out the uncertainty by doing half the range. So therefore, you can work out the percentage uncertainty by doing the uncertainty value, which you've worked it through from working out as absolute uncertainty is range divided by 2. You then divide it by the mean value, you times it by 100, and you should be getting out about 4 or 5%. The next question says, the pressure of a gas is changed and the values for absolute pressure and height of a column of gas are recorded. The data is shown in the table below. The student plots a graph to show how the relationship between the height of the column of the gas and 1 over pressure are shown. Suggest with reasons how the presentation of the graph could be improved and identify any anomalous points. The student also calculates the gradient to be 25 times 10 to the minus 6 kilonewtons per meter. Explain the physical significance of the gradient, state the assumptions and estimate n, the number of molecules of the gas that will be present at a temperature of 298 Kelvin. So pause the video now, then unpause the video when you want to go through your answer. Right, so firstly, how could you work this all through? So the presentation, looking at it, the x-axis scale could go with a more appropriate scale. The y-axis should be made larger so that more plotted points cover over half the grid. You should have the plotted points growing precisely with crosses. The line of best fit is probably too steep. The third data point is anomalous. You have to have error bars onto the plots, and you should have units on your y-axis. If you think of the equations PV equals nRT, well therefore 1 over P equals V over nRT. We know volume is area times by height, and the gradient therefore of the line is area over nRT. So therefore we can rearrange it to work out that the number of moles is going to be equal to A over RT times by the gradient. That allows you to work it through to be 1.4 times 10 to the minus 3 moles. Our assumptions are the gas is ideal, it is monoatomic, it is no interactions between each other, the particles have a negligible volume, they have perfectly elastic collisions, and the time taken for any collisions is considered to be negligible or extremely small. The next question says, the escape velocity is the minimum speed needed for an object to escape the gravitational field of a planet. An object travelling at the escape velocity has a kinetic energy equal to the magnitude of its gravitational potential energy at the surface of the planet. Show that the escape velocity v for a planet of mass m in radius r is given by the expression v equals the square root of 2gm over r. Then show that the escape velocity for a mass of the Earth's surface is about 1.1 times 10 to the 4 meters per second. Then when the Earth formed, a large proportion of the gas in the Earth's atmosphere was hydrogen. Explain why the hydrogen gas is no longer a large proportion of the Earth's atmosphere. At 20 degrees, the root mean square speed is 1900 meters per second for hydrogen. So pause the video now, then unpause the video when you want to go through your answer. Right, so what we can say is we can say that the energy is equal to m times by the change in potential, which is equal to gmm over r. We can therefore say a half mv squared, which is the change in energy, is equal to gmm over r. So therefore v is equal to 2gm over r. So therefore v equals the square root of 2gm over r. You can pop in all your values given in the previous question. You work it all through. G is given on the equation sheet, and we get 1.12 times 10 to the 4 meters per second. Now, you've got to understand that even though you've got a root mean square speed, that's actually a range of molecular speeds. Some molecules will travel much faster than 1,900 meters per second, while some will be traveling a lot slower. It's just an average speed. So there'll be some molecules that will have a greater speed than the escape velocity, which is 1.12 times 10 to the 4 meters per second, and therefore there'll be some molecules with a high enough kinetic energy to escape, which is why lots of that hydrogen gas has left the Earth's atmosphere. The next question says a cylinder contains 40 decimeters cubed of carbon dioxide at a pressure of 4.8 times 10 to the 5 pascals at room temperature. Calculate the number of moles of carbon dioxide, the mass of carbon dioxide, then calculate the volume of 1 mole of ideal gas at a pressure of 1.01 times 10 to the 5 pascals at a temperature of 0 degrees Celsius. Then a vessel of volume 200 decimeters cubed contains 3 times 10 to the 26 molecules of a gas at a room temperature of 127 degrees Celsius. Calculate the pressure exerted by the gas on the vessel walls. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one we can say N equals PV over RT, the ideal gas equation. Remember to change to work out what the room temperature is. That's 20 degrees Celsius or 293 Kelvin. Pop it all through, 7.9 moles. We can work out, when you work it all through here, we can say, well, we can work it by saying N equals PV equals nRT, and we can work out what that value is going to be, 7.9 moles. We can then work that through by saying it's 350 grams by using our relative molecular mass, because mass equals moles over mR. Now the next question we can say, well, V equals nRT over P. Pop in all the values, work it through, 22.4 decimeters cubed. Here again, P equals big N KT over V. Pop in all the values because now you've got N, which is the number of molecules in the question. Pop it all through and then you get your answer. Remember, temperature is going to be in Kelvin, not degrees Celsius, 8.31 times 10 to the 6 pascals. The next question says, explain what is meant by an ideal gas. Then a cylinder contains 500 grams of helium at a pressure of 5 times 10 to the 5 pascals at a temperature of 27 degrees Celsius. You may assume that helium acts as an ideal gas. So the number of molecules of calculate the number of moles of helium the cylinder holds, the number of atoms of helium the cylinder holds, calculate the volume of the cylinder. When the tap of the cylinder is open for a short time, a small amount of helium escapes into the atmosphere. As it does so, the temperature of helium drops significantly. Explain why the temperature drops, then describe what happens to the average speed of the atoms of the escaped helium. So pause the video now, then unpause the video when you want to go through your answer. Right, definition of an ideal gas, you've got to learn it. It's a gas that obeys the ideal gas laws at all temperatures and all pressures. In this next one, it's 125 moles because we've got the, we know the mass of the helium is 500 grams and we know what the MR of helium is, it's 2. So moles is mass over MR, 500 divided by 2 is therefore going to be 125 moles. Multiply that by Avogadro's constant, the number of molecules in 1 mole to get the number of molecules, 7.53 times 10 to the 25 molecules. We can then work out the volume because V equals nRT over P, pop in all the values, and we get 0.62 times 10 meters cubed. Remember, temperature is in Kelvin, not in degrees Celsius. The temperature drops because what happens is the helium does work on the atmosphere because it's going to expand into the atmosphere, so energy is taken from the helium as it expands out, so therefore its temperature will drop. Remember, that work is done when it compresses and work is done out of it when it expands, and then as the temperature goes down, well, therefore the kinetic energy goes down, so the average speed of the particles will drop. The next question says, a hot air balloon is basket and passengers have a total mass of 540 kilograms. The inflated balloon holds 3,000 meters cubed of air. Calculate the minimum force needed to lift the balloon off the ground. Atmospheric pressure is 1.03 times 10 to the 5 pascals and the density of air at this pressure is 1.23 kilograms per meter cubed. Calculate the mass of 3,000 meters cubed of air. Calculate the number of moles of air in the balloon. You may consider the air of this pressure to act as an ideal gas with a relative molecular mass of 29. As the air is heated, it expands. Some of it is expelled through a vent at the top of the balloon. Calculate the maximum mass of the air that can remain in the balloon to give sufficient upthrust for the balloon to just leave the ground. And then calculate the minimum temperature that the air inside the balloon must be heated for the balloon to just lift off the ground. So pause the video now, then unpause the video when you want to go through your answers. Right, in this next one, what's the minimum force required? Well, it's going to be equal to the weight of the object. So 540 times by 9.81 is 4,410 newtons. In this next one, we can work out what the mass is going to be by doing mass is therefore going to be equal to density times by volume. We've got the pressure, and we can work it all through. We've got the density there. We've got the volume. We can work it out. So therefore, it's going to be 3,690 kilograms. Now, the number of moles is therefore going to be mass over the mR. So you can work it through that way. That gives you the number of moles to work it through. And then the next bit here is to achieve the lift, a minimum of 450 kilograms of air must leave the balloon. So therefore, the maximum mass of the air remain to be 3,690, which we've worked out as the mass of the air, minus 450, which is 3,240 kilograms. And then the remaining air is therefore going to be divided therefore by 29 times 10 to the minus 3 to work out our number of moles. PV equals nRT, so therefore T is going to be equal to PV over nR. We've got all those values, so it's 332 Kelvin, which is 59 degrees Celsius. The next question says 0.24 moles of gas is contained in a cylinder as represented. The gas is trapped by a disc of negligible mass so that the pressure in the cylinder is equal to the atmospheric pressure outside the cylinder. The disc can move up and down the cylinder without friction. Use the data to show that the length is approximately 1.2 meters, assume ideal gas behavior, and explain your reasoning. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, how do you work it through? Well, we can work out what the volume is because it's 5 times 10 to the minus 3, which is going to give you your area times by the length. We know PV equals nRT, so therefore we can substitute that volume into that equation of PV equals nRT. Pop it in, and then you got your values for N, R, and T. Remember, temperature is in Kelvin, okay? And then we've got pressure given as well, so you can pop them all through to get L to be equal 1.19 meters. The next question says, an airbag is a safety feature used in cars. Nitrogen gas is released into an airbag. The airbag inflates to a volume of 7.08 times 10 to the minus 2 meters cubed. The pressure of the inflated airbag is 1.24 times 10 to the 5 pascals. Show that the number of molecules of nitrogen gas released into the airbag is about 2 times 10 to the 24. Nitrogen gas escapes from small holes in the inflated airbag. The pressure is decreased to 3.45 times 10 to the 4 pascals. Calculate the number of nitrogen molecules that escape from this airbag. The volume and temperature remain constant. So pause the video now, then unpause the video when you want to go through your answer. Right, we know PV equals big N KT, so therefore N is going to be equal to PV over KT. Pop in all the values. Now again, remember that we work our temperature out in Kelvin, not degrees Celsius. So pop on all the values and you get 2.13 times 10 to the 24. We can therefore say for this next question that because we know the volume and temperature remain constant, well then the pressure is directly proportional to the number of nitrogen molecules in the bag. So therefore P2 over P1 equals N2 over N1. So you can work out what N2 is, pop in all the values, and we get N2 to be 5.93 times 10 to the 23 is the number of molecules. But it wants to know how many molecules have left the bag. So you do the start number, 2.13 times 10 to the 24, minus the final number, 5.93 times 10 to the 23, so 1.54 times 10 to the 24 molecules have left the bag. In the next question, a toy rocket is made from 1.5 litre plastic bottles with fins attached for stability. The bottle initially contains 0.30 litres of water, leaving 1.2 litres of trapped air at temperature 17 degrees Celsius. A pump is used to increase the pressure of the air within the plastic bottle to 2.4 times 10 to the 5 pascals at the start of liftoff. Figure 1 shows the rocket at the start of the liftoff. Calculate in moles the number of trapped air amount of trapped air in the bottle at the start of liftoff. The trapped air pushes the water downwards out of the hole, causing the rockets to rise. The temperature of this air remains constant. Calculate the final pressure of the trapped air just before all the water has been released. Use the data on the toy rocket to show that the upwards force on the rocket at the start of liftoff is about 15 meters, and then hence the initial vertical acceleration of the rocket. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know N equals PV over RT. Pop in all the values. Remember, T is in Kelvin, so it's 0.12 moles. We also know from Boyle's law that PV equals a constant, or P1V1 equals P2V2. Pop in all the values, and P equals 1.92 times 10 to the 5 pascals. Now also we can know that the change in pressure is going to be equal to 2.4 times 10 to the 5 minus 1 times 10 to the 5, so it's 1.4 times 10 to the 5 pascals from the information given. We know that force is equal to the change in pressure times by the area, because pressure equals force over area. So you can work that through. You've got the area, so you get 15 newtons. And then finally, what's the initial vertical acceleration of the rocket? Well, the total mass of the rocket is 0.35 kilograms. F equals ma, where F is going to be the resultant force, which is the upwards force minus the weight downwards. So you can work it all through and you get A to be 34 meters per second squared. The next question says, calculate the average speed of the helium molecules at room temperature and pressure. Comment on how this speed compares to the average speed of air molecules at the same temperature and pressure. Then a sample of neon is contained in a cylinder at 27 degrees Celsius. Its temperature is raised to 243 degrees Celsius. Calculate the kinetic energy of the neon atoms at 27 degrees Celsius, 243 degrees Celsius, and compare the speeds of the molecules at the two temperatures. So pause the video now, then unpause the video when you want to go through your answer. Right, we know that P equals 1/3 P times by C squared, so you can pop in all the values and you get the speed out to be 1.69 times 10 to the 6, which when square rooted is 1,350 meters per second. Now, that's considerably faster than air molecules at the same pressure, because helium has the much smaller mass, so to have the same kinetic energy, which is the same for the same temperature, they've got to have a much greater speed. Now, in this next one, we know that the kinetic energy is 3/2 kT, so we do 3/2 times by K times by 300, the temperature in Kelvin, so it's 6.2 times 10 to the minus 21 joules. Do the same at 243, but remember now we convert our temperature into Kelvin, so it's 1.0 times 10 to the minus 20 joules. Now the ratio of speeds is going to be 1.07 over 0.62 by looking at the two values given before, so therefore the ratio of energies is 1.72. We know that speed links into energy by a square root because it's a half mv squared, so therefore it's going to be 1.31 to 1. The next question says, a truck is used to cross the Sahara Desert. The journey begins just before dawn when the temperature is 3 degrees. The volume of air held in the tyre is 1.50. It exerts a pressure on the tyre walls. Calculate the number of moles of air in the tyre. By midday, the temperature has risen to 42 degrees Celsius. Calculate the pressure in the tyre at this new temperature. You may assume that no air escapes and the volume of the tyre is unchanged. Calculate the increase in the average kinetic energy of an air molecule due to this temperature rise. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this question, how do you answer it? Well, in this first one, you can see that it exerts a pressure by the kinetic theory as the molecules hit the wall and rebound from the wall. Each impact causes a small force or change in momentum and impulse on the wall. So the molecules are in random motion, so the more impacts will smear the force over the whole wall. Now the number of moles, we can say, well, ideal gas equation, PV equals nRT, N equals PV over RT. Again, remember, temperature should be in Kelvin, not in degrees Celsius, so we get 224 moles. Again, we can use PV equals nRT, so P equals nRT over V. Pop in all the values. T is in Kelvin, not in degrees Celsius, so it's 3.91 times 10 to the 5 pascals. We also know that kinetic energy is 3/2 kT, where the change in energy will be the change in temperature, so therefore you can pop it all through, and remember it's a change in the kinetic, the temperature in Kelvin, so therefore it's 8.01 times by 10 to the minus 22 joules. The next question says, explain what is meant by Brownian motion and how it provides evidence for the existence of molecules. The density of air at room temperature and pressure is 1.21 kilograms per meter cubed. Calculate the average speed of air molecules at this room temperature. State and explain the effect on the average speed of the air molecules of raising the temperature of the air but going to a higher altitude but keeping the temperature constant. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, Brownian motion is the random zigzag motion of larger particles. So the air or water molecules will collide with these bigger particles. Each collision gives the larger particle a change in momentum or an impulse which will make it move in a different direction. This next one we can do P equals 1/3 PV C squared, so you can pop in all the values and you get 2.55 times 10 to the 5 as your C squared, so therefore C is equal to 505 meters per second. If you raise the temperature, well, temperature is directly proportional to the kinetic energy, so the speed will increase. Now going to a higher altitude, the speed will be unchanged because you're not actually changing the energy of the particles when you have a higher altitude because the temperature is remaining constant. The next question says, a student placed a metal block of mass 220 grams in boiling water at 100 degrees Celsius for several minutes. The student then transferred the metal block into 300 grams of water at 90 degrees Celsius inside a glass container of mass 50 grams. The final temperature of the water was 23 degrees Celsius. The table shows specific heat capacity values for copper and tin. Deduce whether the metal block was made from copper or tin. So pause the video now, then unpause the video when you want to go through your answer. Right, so the energy lost by the block is the energy gained by the water in the glass. So E equals mc times by change in temperature. So it's the mass, which is 0.22 kilograms, going from grams into kilograms, times by C, times by that change in temperature. So you can work it all through, and then you can see that actually you can then link it into the energy gained by the water and by the glass. So it's 0.05 times by 840 times by 4 plus 0.3 times by 4,200 times by 4. So we can write an equation out and say 16.94 C is going to be equal to 5,208 joules. So therefore C is going to equal to 307 joules per kilogram per Kelvin. So as you can see from the previous table, as it is 307, the answer is going to be copper. The next question says, an electric kettle contains 4.25 times 10 to the minus 4 meters cubed of water. The temperature of the water is 22 degrees Celsius. The kettle is switched on. The water takes 85 seconds to reach a temperature of 100 degrees Celsius. Show that the power of the kettle is about 1600 watts. Then the water boils at 100 degrees Celsius. Calculate the time now taken for 75% of the water to boil away. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can work out the mass because we've got the density, we've got the volume. So mass equals volume times by density, so it's 0.424 kilograms. We know that the change in energy, because it's change in temperature, is mc times by change in temperature. So therefore it's 0.424 times by 4,190 times by the change in temperature, which is going to be 78. So we get 1.386 times by 10 to the 5 joules. Power is change in energy over change in time. We know the time is 85 seconds, so it's 1,631 watts. In this next one, because we're boiling, we're changing state. So now we say the change in energy is equal to the change in mass times by the latent heat capacity. So you pop in all the values and you get energy to be equal to 7.19 times 10 to the 5 joules. Now again, you can remember that it's taking the time for 75% of the water to boil away. So if you noticed, okay, we can work it through that way because we've taken 75% of the water from the previous question. So we've done 0.75 times by 0.424. Now time is the change in energy over the power, so you pop it all through and you get 441 seconds. The next question says, a student investigated the relationship between the pressure and the volume of a fixed mass of gas at a constant temperature. He used his data to plot the following graph. The student stated his graph demonstrated that the pressure exerted by the gas was inversely proportional to the volume occupied by the gas. Assess the validity of the student's statement. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you want to do is, if they are in fact inversely proportional, you should be multiplying the values of the y-axis and the x-axis, so find the points where they intersect the coordinates of the line, and then they should all equal the same value. So again, when p equals 110, v equals 0.006, so you can times together 660. Next, further down, when p equals 60, where v equals 0.011, so therefore it's 660 again. And then when p equals 51, v equals 0.013, multiply them together, 663. So the value of the two numbers as a product is constant, so therefore inversely proportionality is proven. That again, you should be doing at least 3 values to show that. The next question says, a sealed container contains n moles of an ideal gas. The gas has a pressure P, an absolute temperature T, and occupies a volume V. The mass of 1 mole of the gas is big M. Use the ideal gas equation to show that the density of the gas is given by the expression ρ equals Pm over RT. An airship has a cabin suspended underneath a gas bag inflated with helium. The airship is floating above the ground and is stationary. The volume of the gas bag is 12,000 meters cubed. The temperature of helium in the surrounding found in air is 20 degrees Celsius. The atmospheric pressure is 1 times 10 to the 5 pascals. The molar mass of air is 0.029 kilograms per mole. The volume of the cabin is negligible compared to the volume of the gas bag. Show that the density of air under the conditions described is about 1.2 kilograms per meter cubed. Calculate the weight of air displaced by the airship. Explain why the weight of the air displaced by the airship has the same magnitude as the weight of the airship and its contents. And the pressure of helium in the gas bag is maintained at a value only slightly greater than the atmospheric pressure. Suggests why a larger pressure is not used. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, we can say ideal gas equation, PV equals nRT. The mass is the number of molecules times by, so the number of moles times by the number of molecules in there. So therefore, we can substitute in the equation, cancel them all through, and we'll get rho equals PM over RT. In the next one, we can then work it through using the equation. So we can say 100,000, because we're converting kilopascals into pascals, times by 0.029, which is the molar mass. Okay, then divide by 8.31 times by 293. Temperature goes into Kelvin, so 1.12 kilograms per meter cubed. The mass of the air is going to be the density times by the volume, so you can work it through that way, as you can see in there. And then you can change that into a weight by times and by G, 9.81, so therefore we get 140,000 newtons. In the next one, we know that when something is floating in the air, the upthrust will equal to the weight of the fluid or the air that are displaced. So therefore the airship is in equilibrium. We can tell that from the information given in the question. So therefore the resultant force is 0. So the upthrust must equal the weight of the airship. And then finally in the last one, the greater pressure would increase the density or the weight of the helium. And increased pressure but no change in volume would therefore have no more upthrust. So if the volume does go up, then the upthrust would increase. Now the pressure only does need to be large enough to inflate the gas bag, and an increased pressure may then cause a structural failure in the actual component with that increased pressure. So that brings an end to our revision session today. So hopefully if you've been successful, you can answer A-level physics examination style questions for thermal physics. You can assess your understanding on A-level physics, and you can understand what topics need to improve upon for A-level physics in the thermal physics topic. So thank you so much for attending this revision session for AQA A-level physics on thermal physics. Thank you so much and have a lovely day.